Hey guys, so for lesson 6.3, this starts out with coming back to an idea that we have run into earlier this year about parametric equations. So I wanted to take a minute, and really the math on this is fairly simple, but I wanted to kind of help you wrap your head around the idea of these parametric equations and why they are what they are and kind of how these work. So we're going to take a quick look at page 467 out of your textbook so we can discuss this a little bit. So here's what this paragraph looks like. So this is a pretty good description of parametric equations and how they work, and it also references the earlier sections in our book for where we've talked about this before. And we even had at least one test question I remember from previous tests that had us use parametric equations. So it's talking about these vectors used to solve problems of motion. And the issue is when you have a two-dimensional vector like this, right, where x represents the horizontal component and y represents the vertical component, in motion problems, vectors vary as functions of time, right? In other words, this is some function of time in the horizontal direction, and this is some function of time in the vertical direction. The issue is time can affect each component in a different way. So it's not just one function of time that represents both components. They can be affected differently, right? So what this is saying right here is my x component, my horizontal component, can be affected by this function of time, whereas my vertical component could be affected by a completely different function of time, right? So when we sort of graph these or look at real points as values of time, we have to look at each function separately and look at their own functions and how they're affected. Right, and so then they kind of go on to describe, here's how we've talked about this before, here's some previous sections, some links to some trig that we've looked at in the past with unit circles from chapter 4, on and on and on. So this is the definition box of that. And so here's kind of what I wanted to show you on this. So we're looking at the two different functions over some interval of time is creating this curve. And so they're talking about I representing whatever the interval of time is, and then t would represent the values of time within that interval. And that's what generates this parametric curve. So what I want to do is take you through one of these. And this was my own description of this, kind of in my own words to try to simplify things a little bit. So again, this is kind of the key issue here is there is a common variable of time in both functions, right? They're using the same variable. So whatever t represents, that's the time for both components. But the issue again is it affects each component differently. They each have their own function. So here's a good description of that. So if I have a vector where x is my horizontal component, y is my vertical component, well, what we would be doing with that is we would be looking at, okay, what are the results if I plug in certain values of time? So again, you can see here, though, is how this horizontal component is going to be affected differently than the vertical component. This one is a linear function, right, with a slope of 3. This one is a parabolic function, right, because it's a quadratic. So the effect that time would have on each component is different. And so we have to look at each one separately. So here's just a simple interval for time. So it's saying that time is from -2 to +2, inclusive. And so we're going to see what this graph would look like as I plug in this function of time into two different functions. Right? So when I plug in -2 for the horizontal component, it's going to be affected this way. So -2 squared, which is 4 minus 2 is 2. So that tells me where we are in the horizontal component at -2. In the vertical component, when I plug in my -2 for time, I get -6. And so as we keep generating these values within our time interval, again, we're just having to plug them into each component separately to see how it gets affected by that period of time. So as we plug in -1 into the x component, -1 squared is 1 minus 2 is -1. -1 into this guy would be -3. 0 is nice and simple. Plug in that 1. And you'll see in the parabolic function we start getting these repeating numbers because of the t squared, whereas in the vertical component it's a linear function. So these are going to travel in a linear fashion as they're continuing to go up 3, up 3, up 3. So if I plug in the 1, I get this, and plug in 2, I get this. So you can see these are all in a linear path going up 3, whereas these are in a parabolic path and being repeated values. So 2 squared was 4 minus 2 is 2. And so you can see what we got going on right there. So let's graph these guys. So if I just plot the points, so at 2, negative 6, we got negative 1, negative 3, negative 2, 0, I got negative 1, 3, and 2, 6. So you can see the, so you can see the curve that's generated by those points looking like this. And so that is the parametric graph, the parametric function created by these two different parameters that we have for our horizontal component and our vertical component. So obviously it does not take the traditional linear or parabolic path that we're used to seeing with the parabola, right? So it still has that parabolic path, but obviously since the vertical component is different than the horizontal, right? It's taken on quite a different path than what we would have seen with either one of these separately. So I want to show you something real quick, because here's what's going to happen moving forward. Obviously, it's a little tough and tedious to deal with each component separately. So here's what we have actually done in the past with these, is what if I combine my two equations. Let me scroll up a little. I combine these two equations into one function that would give me this graph. So instead of having to look at these separately, how can we combine these and put them together and actually get the equation for just this one function rather than two separate components like we see here? So what if I'm going to isolate my value for time in the x function so I can plug it into this value of time and get one function for y equals whatever the parametric function is. So in this one, if I were to add the 2 over and then square root both times, both sides, that would tell me that t is equal to plus or minus the square root of x plus 2. So I'm just getting t by itself. So that's all I did. And I'm doing that so that I can now plug it into my y function for t to actually identify the equation of this parametric function. So now I have plus or minus 3 times the square root of x plus 2. So watch what happens when I plug in this function into my calculator. If I did this correctly, I should now get this graph that we just did. So let me try to get all that onto one page. Actually, I'll just bring it down. Let's do this. I'm going to slide u over. So here was the function that we just came up with. And I'm going to put that into my calculator. So I have the positive 3 root x plus 2. I also have the negative 3 root of x plus 2. All right, there's my graph, and I'm going to set my window settings to go only from the 6's on the x-axis to the 6's on the y-axis, so I can kind of box in this image so that you can see it should look exactly like what we graphed on our graph. So let me go ahead and hit graph on that. So here's the positive side, and then here comes the negative side. So there you go. So you can see now that we've identified this equation, we can now graph just this one equation in order to get this function right here, rather than having to plug in all these points into different parameters. So that's what's going on in the next section. Sorry, let me flip the page for you. So that's now what's going on here, where they're saying, okay, here are the two different components, but let's get this into one equation here. So let's isolate t within the x component and then sub it into this t into the y component so that I get one function. So right here they isolated t on the x component and they came up with that statement right there. They're now going to take this equation and plug it into t into the y function in order to get that statement right there. And so now you have one function identifying the parametric function, like I just did on the previous page. Let's try that. We're going to try that on one of these guys. So for number 6, and as always, maybe a great time to pause and give one a try on your own if you'd like. But again, I'm going to take the x function, I'm going to isolate t, so I can identify t as x plus 2. And I now want to take that and I'm going to sub it in for t into the y function. So 1 plus 2, x plus 2 squared. Now gives me one function for the parametric equation. And now I have this guy right there. And yes, you could do some simplifying on this, but I kind of like this one. This is actually now kind of in vertex form like we've seen before. So I can actually look at this and identify my vertex is going to be negative 2, 0. This has been vertically shifted up 1. And it has a vertical stretch of a factor of 2. So I could actually graph this pretty easy now, knowing what we've learned already up to this point using those transformations. So we could do it on a calculator, but like I said, we really shouldn't have to at this point, now that I know how to deal with that kind of an equation. All right, let's take a peek at this guy. So this one is now using some of our trig functions. So for this guy, one thing that they're talking about on this is kind of a mixture of some things we've talked about this year with, in theory, something that you've learned in the past as equations of a circle. So either in geometry and or algebra 2, you should have dealt with the equation of a circle. So let me take you back for a minute in case you don't recall what that looks like. But basically the equation of a circle looks something like this. So maybe this will look familiar to you. But this is the equation of a circle. And so the idea is h and k represent the center of the circle. And of course, r is the radius of that circle. Well, if you're centered at 0, 0, then h and k don't need to be there. Therefore, if I'm centered at 0, 0, the equation of the circle is simply x squared plus y squared equals r squared. Right? That's like the most basic parent function look for the equation of a circle when you're centered at 0, 0. And so what they're saying on this one is, since my horizontal component is a cosine function, and the vertical component is the sine function, we're recognizing that I should be looking at a circle when we're doing that, because based on all the trig things that we've already looked at, consider your unit circle, all those have dealt with the cosine representing the x, the y is your sine value. And so they're looking at this saying, okay, this looks like the equation of a circle because of the cosine is my x and the sine is my y, so let's identify this in a couple ways. One is they're saying, well, first things first, even if I didn't know this was a circle, I still have learned that sine squared plus cosine squared equals 1. Right? And so if nothing else, I can use that identity to start simplifying these guys and combine them into a single function. Right? So we're plugging into this formula, and they're doing their cosine squared plus their sine squared equals a value of 1. Now in this case, they're saying, well, because we recognize that this would have to represent a circle, based on what we just talked about, with these guys representing my x and my y, let's take this idea and set it equal to the equation of the circle. So in other words, these components represent the radius. Right? So this is how far it goes to the right, this is how far it goes up, and that represents the radius of our circle. Really what this comes back to is some good old-fashioned Pythagorean theorem. Right? When we look at our unit circle, and all this comes back to the idea of right triangles in a unit circle where, and remember this is how it's always been, so if this is my circle, do it this way. So anytime I have had a radius within that circle, like if this is my radius, well, how did we get there? We've had a horizontal component, which is our cosine. We've had a vertical component, which is sine. And what do we always know about this, right? Well, if this is a right triangle, then cosine squared plus sine squared equals r squared. So really the equation of a circle simply comes from basic Pythagorean theorem, right? That's all that really is, right? So it's just saying that we're always linking our cosine to our x value. We're always linking our sine value to our y value. And it's just the equation of a circle, right? The hypotenuse of that triangle is the radius of the circle. And so it fits directly into Pythagorean theorem and becomes the equation of the circle. And it's always in terms of the radius, right, that we can see right there. So they're saying, okay, here is our setup right here. We can set it equal to the equation of a circle. This is all, again, just basic Pythagorean theorem, right? So x squared plus y squared equals my circle. And so when they go to clean this up, what they're seeing is, as you simplify all this, so I squared both, it becomes this. They factored out the 9 as the greatest common factor. That leaves me with sine squared plus cosine squared, which we know is 1. Looks like this. So if this represents r squared, the radius of the circle, right, r squared, well, the square root of r squared tells me what the radius actually is, right? When we write this, what we're seeing on the right side of this equation is the radius squared. So if I ever want to know actually what the radius is, I have to square root this number in order to get the radius, right? And so that's the extra step that they took right here to say, oh, okay, my radius is 3. So here's the equation of the circle. It's just x squared plus y squared equals 3. And so, again, they've now taken these two different parameters and combined them into a single parametric equation to identify a single graph. So I hope all that made sense, and hopefully you'll recall a little bit of what you've seen in the past in regards to the equation of a circle. All right, so now I want to bring you back to something that we talked about on the very first lesson of this chapter, and that was, what is the result of adding two vectors together? So if I have vector PQ, and I want to add to that vector QR, what is the resultant? And that would be this guy right here, PR, right? The super key idea in this, and making sure that we always get this correct, is the connection right here. Where this first vector ends is where the next vector begins. And that has to happen in order for this equation to work, right? They have to be connected, right? So essentially it's like we're cutting out the middleman, right? I'm going to take this guy and smush it together with this guy in order to get the ending result right here. So it's like the middle guy that they had in common is no longer needed. We kind of smushed them together to make one statement. So it started at point P and eventually ended at point R. And that's why we say the vector is PR, right? It started at P and ended at R. And so that's where we're getting the dotted line, the dotted vector, which is our resultant, right? So remember, the idea on this, and we've talked about this before, but let's just say you're here. This is you. You're standing here, and this is the other side of the river, and I need to get from here to here. Well, if the river is flowing this direction, right, like this, I can't just jump in and swim straight across, or I'm going to end up way down here because the current is going to push me down to this point right here. So what I would actually have to do is I would have to swim this direction. So as the river pushes me this way, I go straight across to the point I'm actually aiming for, which is this guy, right? So this is like my swimming plus the current of the river is going to put me at this point on the other side. Okay, so anyway, let me go on to this next guy. It's a lot to write down, so obviously if you don't have my printed notes, first of all, you should have my printed notes, but if you don't, you can always reference this on page 470 instead of trying to copy down everything that you're looking at. So find a parameterization of the line through point A and point B. So all we're really getting to start with is a point right here at negative 2, 3, and a point right here at 3, 6. And our deal is to come up with a function that describes this as a parametric equation. So really what we're going to see at the end of all this, what I'm really getting out of these points from A to B is really the equation of a line. Right? That's really all this comes down to. Now it looks kind of funky because it's in terms and vectors, so we're not used to seeing it this way, but that's really all it is. So let me walk you through this. So here was the point I started with, point A, here's point B. So if I can see this as a vector from A to B, right? It's kind of an ongoing vector. Right, that's what we're starting with. So what we're doing is we're going to say, well, let's just pick any point that would be on this line. If this line continued, if this vector continued, we're going to identify just a general point that could represent any point on this line. I don't want a specific one. I want a general one so that this could apply to any point on the line. So I'm just going to say it's point P, right? And so it's some X component and some Y component. So it could be any point on this line. So that's what we're identifying this as. So if we just put this here as kind of an extension of this vector so you can see it separate, then how do we identify the equation of this vector? So as I look at these guys, what you always want to link this to is the origin, right? That's kind of what makes this work. So we want to see this as starting from 0, 0, and how do I get to here? Well, if I'm starting at 0, 0, then the vectors I'm looking at would be from OA, that's where we're starting, and then it goes to AP. And so if I add those two vectors together, I'm looking at vector OA plus AP would equal what? So here's the setup, and here's what we were just talking about up above. So if I did OA plus AP, again, notice the connection, the interior connection right here is the A. So I started at O, and eventually I ended at P. So if I smush those together, I get vector OP. Right? So now we have kind of the generalized vector from the origin to any point on this vector. Okay, so since AP runs the same direction as AB, so here's vector AB, OP, which represents from the origin to any point on that vector, right? Whatever this point is, it is simply going to be a scalar multiple of vector AB. In other words, it's going the same direction. It's just either going to be a bigger vector because it's going to be a point out here, or it's going to be a shorter vector because it could be a point closer to A, right? But because it's always going to run the same direction, it's simply going to be some scalar multiple of this. In other words, it has the same direction, but not necessarily the same magnitude as that one does. So here's what I want you to, here's kind of the big connection here that we got to make. As I look at this equation, so look at AP, so what we're saying is that AP is simply a scalar multiple of AB. So in other words, if T represents the scalar, right, so I have some scalar times vector AB is going to equal whatever AP is. So we can sub out AP in this formula for AB times some scalar. So there's kind of the big connection. So we get that substitution, and now really what you're looking at is the equation of a line, y equals mx plus b, where OA represents like your starting point, right, the beginning of this line, and AB acts as like the slope of the line, right? So if you're looking at this as kind of a y equals mx plus b, this is like the y function, right? This is the main function, the result, which is OP. It has a beginning point, and then it's like an mx. So whatever my variable is, x, right, is being multiplied times the slope, which is AB, which is the direction vector, right? So my initial point was OA, and my slope, or the direction of the line, is AB. And then T can represent any variable of time that we want to plug into that. So again, I hope that makes sense, but if you can link it to y equals mx plus b, which is really all we're doing, but in terms of a vector, hopefully that makes sense. So again, do recognize this AB as the direction vector, right? It's the slope or the direction that we're traveling. This is the starting point. So anyway, so to get the components of AB, we're looking at the terminal point minus the initial point, right? And as you see vectors in physics, maybe some of you guys already have, that's kind of a big statement that we use quite a bit to identify the components of a vector is terminal minus initial. So if I look at vector AB, so this one right here, if I want to get the components of this guy, in other words, how far did it go to the right and how far did it go up? Well, if I want to know how far this thing went to the right, I would do this x coordinate minus this x coordinate. And if I wanted to know how far I go up, I would have to do this y coordinate. Sorry, I'm losing my words. I'm overlapping too many words with components and coordinates. I would have to do this y coordinate minus this y coordinate, right? So that's really all we're doing is we're just subtracting their corresponding parts, right? So I'm going to find the difference in their x's to see how far we went this way, and I'm going to find the difference in their y values to see how far we went this way. And hopefully that sounds familiar. That's exactly what we do for slope, right? Y minus y over x minus x, right? So really this is really big connection to what we've done in the past with equations of lines and slopes. So the goal right now is to take this general equation and replace it with some real numbers. In other words, for vector OA, I want to replace that with his components. And for vector AB, I want to replace that with his components. Well, OA we already know. That was given information. So if you look back at vector OA, that was the points -2, 3. Right? From the origin, we went left 2 and up 3. So this is the component form of vector OA. So what we need is the component form of our direction vector AB. They didn't tell us what AB was. They told us what A was. They told us what B was, but they did not give us a component form for vector AB. So we need to take vector AB and put it into component form, just like what I set up above. I'm going to do point B minus point A. So I'm going to do x minus x right here. And I'm doing y minus y right here. So I'm finding the difference in their x's to get the horizontal component. And I'm going to find the difference in their y values to get the vertical component. So that I can actually replace this guy and this guy with some real numbers. Right? So this was my initial point. We now figured out the component form of AB, and that is our direction vector. So again, if you were to start at point A at -2, 3, and you went right 5 and up 3, you would now be on point B. So we have now just identified, basically in slope-intercept form, so it's like y equals mx plus b, the equation of line AB, but in terms of vectors rather than in terms of like slope and point. But what I'm hoping that you'll see on this is why this is what it is, right? It's the same thing as y equals mx plus b, but we don't call this m, right, the slope, even though that's really what it is. The slope tells me the direction of a line, right? And so this is our direction vector, right? It's the slope of the line. It tells how far we go right and how far we go up, just like slope does. And again, this is our starting point of the line of the vector, right? That guy right there is our initial point of the vector. So anyway, one thing we could do from here, if we actually wanted to get the parameters of this, so one last step is to now get the parameters of this. So our parameters would just be to simplify this. So distribute the t, and then add on these guys to those guys. So I have -2 plus 5t. That's my horizontal component parameter. And if I did 3 plus 3t, that gives me the vertical parameter or component of this vector. So we can write it this way as well. And so now it's kind of like what we started out this lesson with, but like backwards, right? It's now instead of them starting us with this, and we bring it back to one equation for t, we're kind of doing the opposite. And so we're now identifying what are the parameters for each component of vector AB. And so now we could actually, if we wanted to, identify any point on that line by just plugging in a value for t. I hope all that makes sense. I know that was a little lengthy, but I'm really hoping I want you guys to be able to wrap your head around what's going on there. So let me just take you to a couple last problems. So I want to do a few of these guys with you. So this is some review problems that we can do together just to make sure you understand all that we just went through. So I'm going to start with some review questions from the circle problem, and then we're going to do one just like what we talked about a second ago, so you can see another example of that as well. So let me start with one of these guys. Again, as soon as I see that sine is representing a component and cosine is representing another component, and I'm given a domain like this, which obviously represents a circle, we're recognizing the connection on this to the equation of a circle, which is x squared plus y squared equals r squared. Right, so that's as soon as I see that kind of information, I want to connect it to my parent function of a circle. Now this one didn't say from 0 to 2 pi, but it still represents a full circle. If I said go from negative pi to positive pi, well, here's negative pi. And if I travel all the way around to positive pi, I'm still creating a circle, right? That's still one entire lap around a circle. So as we plug this stuff into this formula right here, which again goes all the way back to sine squared plus cosine squared equals 1. In the unit circle, the radius is 1. And so that's where this comes from, and it's all coming back to Pythagorean theorem. So big connection there. So we're just simply going to say my x squared, and I'm going to write it this way so you can see it easier, plus y squared equals our radius squared. All right, so that's kind of the setup right there. So if I clean that up, I'm looking at my 4 sine squared plus 4 cosine squared. So if I factor out the 4, I got sine squared plus cosine squared which we know is simply 1. So if I replace this with a 1, I now get 4 equals r squared, which of course that means the radius is 2, right, of this circle. So now I can kind of put all that together to write the answer, where really you don't even have to identify this. I mean, what we're seeing on this, and I want you to know this, is obviously this is a circle with a radius of 2. Right, that's what we're getting on this. So if I want to write the equation of this circle that I'm seeing right here, I'm going right back to this parent function, and I can now say x squared plus y squared equals 2 squared, which is 4. So that's the way we can now write one equation that identifies both of those put together in one equation and gives us the equation of that circle. Okay, so again, you could do the same thing on this one. I'm looking at this one. This one is only going from negative pi over 2 to positive pi over 2, so it's like a semicircle. But we can still write a similar equation for this. So it's really still writing the exact same equation. We would just have to recognize if you were to graph it, the graph would only go from here to here. It wouldn't take a full lap around like a problem like this would. So we can still see on this, if you follow the same path, our radius is going to be 4. So that means when I go to write the equation, it's still going to be x squared plus y squared equals 16, because that's what r squared is. So I would still have that same equation. It's just the graph itself would be affected if I limit it to only those, to that domain right there. Okay, so let me take you through kind of the tough one that we just went through in the previous example. And we'll do kind of a fill in the blank on this one, so you don't have to write everything down. So here we go. So real similar to the one we just did, which is kind of our practice problem here. So I have point A, I have point B, and we want the parameterization of the line segment with these endpoints right here. Okay, so again, here's point A, and here is point B. Point P represents any point on that line, right? So it can be any point on that line. Again, if I look at vector A, B, we always want to link this to starting at the origin from 0, 0. So let me just go through kind of the steps that we would go through on this from beginning to end. So first we want to identify parameterization of the line that passes through AB. So we're looking for that kind of y equals mx plus b type of an equation that we're getting on that. So just remember, when we do y equals mx plus b, it's like the b is like your starting point, your initial point, and your m, which is your slope, is this guy right here, the vector from A to B. And so that's something we're going to need to come up with. So we're using P as representing any point on that line as it moves along line AB, right, or vector AB. So we can write the vector from O to P, from here to here, as the sum of the other two vectors. So if I were to do OA plus AP, that should give me OP. So OP is the sum of going from O to A and then from A to P. And again, we've already talked about how to add those two vectors together, knowing that they had that common middle piece, telling us that we're starting at O and ending at P, so it should look like this when we put those two together. So now we know that vector AP, so now we're looking as a way to identify this guy right here. So we know that vector AP is parallel to AB. In other words, it's going the same direction as AB. However, it is simply like a scalar multiple of AB. So it's running the same direction as AB. However, it is either shorter or longer, as we identify it as a scalar multiple of AB. So this is the substitution that we made in that previous problem, is we want to replace AP, this one right here, so here's AP. So we want to replace AP with something in terms of AB, right? So again, AP is simply going to be a scalar multiple of AB, right? It runs the same direction, but it's either shorter or longer than AB. If we multiply AB by any kind of variable, it becomes AP. So here's the substitution that we want to identify, right? This is kind of that key step, right? So we want to replace this AP with a scalar multiple of AB. And so we're going to rewrite this as OP is equal to OA plus, and here's that substitution move, we're replacing AP with T times AB, vector AB, so that it looks like this. So now we need to put in some values for this. So OA can be identified as negative 3, 1. Right? That's the component form of OA. It went left 3 and up 1 from 0, 0. Right? So that is the initial point. AB, we got to come up with a component form of this. Remember, this is just like having slope. So in order to get components for AB, I have to do B minus A. So our terminal point minus the initial point. So I'm doing my B values. So as you look at the Y's and the X's, so we always do in component form, this is the X's. So I have to do 3 minus negative 3. And for the vertical, I'm doing 3 minus 1. So there's the setup. Let's clean that up a little bit. So initial point was 3, 1. We have our scalar multiple as our variable in the component form of AB. If I clean that up, it becomes 6, 2. And so there's now the parametric equation. If I want to identify the components of this, this is where you would separate it. So if I distribute the t, so if I combine the horizontal components, I'm looking at negative 3 plus 6t. And I can't write quite that small, but it would look something like this. So that's the horizontal component. For the vertical components, I have the 1 plus 2t. I can't fit that in there, so I'm going to do this. and there's our vertical component. So we can write it as the equation, or we can separate it into individual components. So I hope that helps after seeing some of that. So there's a little more explanation down here if you want to read further, but hopefully having now seen that again, that really helps out. All right, I'm going to end you with one final discussion here. Sorry, this one's a little lengthy, but it's kind of tough to go through, and I'm trying to give you some detailed explanation to hopefully help all that make sense. So we're going to look at this projectile motion. And this one's actually pretty easy if you kind of get the initial thing that I'm going to show you. This actually traces back to something at the beginning of chapter 2. Now let me pull that up for you real quick. So if you go back to page 161, we had talked about this formula for vertical freefall motion. What you're seeing on this is, pretend you're like standing on top of a building and you drop a ball off the side of the building, right? So there's two functions taking place here. One is the height of the ball, right, is obviously changing as time increases. You also have the velocity of the ball is going to change as time increases, right? So a couple things that I wanted to point out on this, because really this is just direct substitution into this formula that we have. So let's just talk about the height of the ball for a minute. So first things first, if I just drop the ball, so S sub 0, since S represents the height, S sub 0 would be the initial height that I'm dropping the ball from. If I just drop the ball, like if I just let it go, the initial velocity would be 0. If I throw the ball down, well, now I have an initial velocity that would be whatever it is that I'm throwing the ball at. Okay, so that's your initial velocity. And then G is our gravity constant. So there's two ways we can look at gravity. If it's in feet, then we would go with 32 feet per second squared. If we're going to do gravity in terms of meters per second squared, then it's 9.8. And so that is being subbed in for G. Notice we're going to multiply it by -1/2. So if I'm going to use, say, feet per second squared, and I plug in that 32, I'm going to get -16 right here. Okay, so keep that in mind as you look at the setup of the next function here. So keep these guys in mind for a minute. Let me go back to this problem. So here's what's taking place. So the initial position, so S sub 0, was 3 feet above the ground. That was the initial position. Its initial velocity, so it's actually being thrown, right? It's not like being dropped. It's like it's being thrown up into the air. So initial velocity, they're telling me, is 25 feet per second. Notice all this is in feet, which means the gravity constant we're using is the 32 feet per second squared. So if we're going to graph this as a parametric function, so we have two things going on, right? We have the height function. So here was the first one that they were looking at. So here was the height parameter. So notice they put in the 32 in place of our gravity constant. Here is the initial velocity of 25. That was this one. And then here was the initial height, which was 3. So if you go back to this equation right here, it's just a formula that we're plugging into. 32 went in for G, 25 went in for the initial velocity, and 3 went in for the initial height. And so that's what we have for the setup of this guy. Now this one is only asking us to give the height above the ground, right? So we're just looking at that height formula that we just talked about. So we have this one right here. Our variable, if we wanted to identify kind of a separate variable on this, obviously the sort of the x coordinate of this graph is being done in terms of time. Okay, and so if I'm just plugging in values for time, then the x coordinate is simply a function of time. So it's a very straightforward, simple, direct substitution here. Okay, and so that's all we're seeing on this. So it's like saying, okay, so what's your x coordinate when your time is whatever? So if my time is 0.5, then my x coordinate is being plugged in for t as 0.5. If it's 0.75, then I'm plugging in 0.75 for t, and the value that's being plugged in is simply my x coordinate, right? So they're just trying to show you with this statement that even though this is being done in terms of time, time is simply, in a graph, represents the x coordinate, and that's all that is. Okay, and so I just wanted you to see how we could set that up and then graph it, and then all we're seeing on this is simply the x-axis is a function of time. And so that's all I wanted to identify with you guys on this one. But that is it for now, so until next time.